GEO, the Group on Earth Observations, is a voluntary partnership of governments and international organizations that's building a interoperable framework for all of these observations known as the Global Earth Observing System of Systems. It has 9 different societal benefit areas that it's addressing, including water, where the target for those activities is to produce a comprehensive set of data and information products to support decision-making for efficient management of the world's water resources by 2015. The strategy that we're going to talk about is what's going to happen after this time period when we have these sets of data. How then do we allow the data systems to talk to each other? How do we more effectively meet the user needs that have been discussed? And at this point in time, we have approached this overall task by subdividing it into 5 different components, one dealing with integrated water cycle products and services, another one dealing with extremes, a third one dealing with cold regions, a fourth one dealing with water quality issues, and a fifth one dealing with capacity development. Now, just to give you a bit of background, the idea of having a strategic approach to water cycle observations is not new. We've been working on this since around 2000, when the Integrated Global Observing Strategy Partnership introduced a water theme, and that then became part of the GEO activities when GEO was started in 2003-2004. And so these documents now are somewhat out of date, and the water strategy is intended to update the documents and move us towards the next decade. Now, as we look at what's happened during the past decade, the GEOSS framework has actually provided us with a lot of benefits. It's coordinated access to information from various sources, and there's a GEOSS common infrastructure which allows people to go and route themselves to data that's not only in NASA, but ESA and JAXA and all of the major space agencies around the world. That system has a brokering service whereby you can go into a single portal and then you can be routed to different sources of data. Sometimes those sources of data will tell you that you have to have a proposal to get access to the data. Sometimes they're free and open, as they are at NASA, but there are different approaches for accessing the data. The GEO program itself advocates full and open data exchange, making the data available with a minimum time delay, and making the data free or available for the cost of reproduction. Another benefit that we've found through involvement in GEOSS is that water is now able to have some joint initiatives with many of these other societal benefit areas. So it's made for much easier communication across sectors. For example, we have activities going on with agriculture. We're spinning up activities with biodiversity and ecosystems. We have contributed to the renewable energy activities, and other plans are in the works for supporting some of these other societal benefit areas. In the new GEOSS water strategy, we're looking at 6 themes. One is to address water security and sustainable development. The second is to support the climate change adaptation agenda. Thirdly, to develop warning systems for hydrometeorological hazards. Fourthly, to improve the welfare of the poor in developing countries by providing them with better access to water information so they can improve their water management. Fifth is to address the water, energy, food security nexus issues. And then the final goal is to support human and environmental health and resilience. We found that in having discussions with the users that there are basically 2 sets of users. There are the users who are interested in the water cycle, as we've heard, with all its complexity and interactions, and they have a certain requirement for research quality data. And then there are the water managers who want estimates of the inflows to the systems, estimates of the uses, so that they can then make sure that all of the allocations are going to be met during every year, whether or not it's a flood year or a drought year or a normal year. They want to make sure that they have water available for their users, and so they have a different sort of requirement for information. It tends to be much more local than the requirements for the global water cycle scientists. We'll just walk through the various variables that are dealt with in the strategy report, and I'm sorry I've pulled out these images without necessarily giving full reference to their source. But clouds and water vapor is an area where we're developing some new initiatives, and a lot of need arises there to have very high resolution observations supported by in situ data, and also being able to measure the drop distribution in clouds so that we can better parameterize them in models. The second variable that's emphasized is precipitation, and of course NASA and JAXA are going to be launching the Global Precipitation Mission in 2014, which will make a lot of new data available, so we'll have a better understanding of how precipitation processes work. Evapotranspiration is another variable that is dealt with in the strategy, particularly as it relates to being able to advise on the use of water that's been allocated for irrigation purposes, the land surface temperatures that are measured by satellites like Landsat 8 are used to generate maps of evapotranspiration, and these in turn can infer just how much water has been applied to crops, particularly during drought periods. Other important water variables include soil moisture, and we're looking forward to the launch of the Soil Moisture Active Passive mission that NASA is going to be launching in 2014. It will be supplementing observations of soil moisture that are coming from the SMOS satellite that ESA is now flying, plus a number of other satellites where people are taking the data and inferring soil moisture estimates from it. The challenge really comes when we come to the topic of river discharge. This graph shows the data which are being accumulated in the Global Runoff Data Center on a year-by-year basis. And it represents the in-situ measurements of river discharge. You can see that in the 1980s, which is roughly what this peak applies to, there was a lot of data coming in, but now in more recent years, there's not as much data coming into the Global Runoff Data Center. And the reason for that is that there are some countries that don't send their data in, but there has also been a significant decrease in the number of hydrometric stations that are taking the observations because countries have budget reductions and they save money by reducing the in situ measurements. Unfortunately, those happen in some data sparse areas, so the data sparse areas continue to get more data sparse. So work is going on now to see if we can try to measure river discharge from space, and also to try to measure the water that's stored on the land from space. Wetlands, for example, play a major role in the ecosystem, and it's important to know how much water is stored in these wetlands and their associated ecosystems. But it's also important to know how much water is stored in reservoirs and in lakes. So the same technology that's being used for surface water store will have application to estimating river discharge. Another area which has been successfully dealt with in the last decade through a mission called GRACE is able to provide monthly estimates of the groundwater variations. The satellite itself measures gravimetric variations, which are arising primarily due to variations in the water that's stored at and under the surface of the Earth. And it's possible with a model then to extract out the proportion of that that's groundwater. And from these estimates, we can identify areas where there is excessive use of groundwater through pumping, and as a result the aquifers are being diminished and are under threat. Cryospheric variables are also important. The retreat of glaciers as the temperatures warm and as the dust that's deposited on the surface of glaciers causes melting are important to monitor. Also, for water availability assessments, we need to have good measurements of snow water equivalent, and that's a priority area for future observations. Water quality is also important, and we can measure some water quality variables from space, particularly when the optical wavelengths are able to identify what is happening with water quality. That's true of chlorophyll, that's true of turbidity and sediments in the water, and several other variables that can be inferred from those types of measurements. It's not a replacement for in situ measurements, it's a supplement to in situ measurements. Sediments can also be measured. This shows estimates of sediment concentration on the River Elbe, measured by a mission that the German Space Agency has, and one can identify where there are high sediment fluxes in rivers through the application of this technology. So there are lots of new capabilities which are there, and over the next decade it's a question of how we bring these together in a concerted way to answer the questions that water users have. Part of this relies on interoperability, part of it relies on integration, and this is a vision that may stimulate new innovations related to integration. It's developed by Professor Koike at the University of Tokyo. He envisions that we would be able to have shared virtual space, perhaps known as a workbench, and this would allow us to bring in data, but it would also allow us to do very sophisticated versions of Google Hangouts, where people would be able to share their experiences and work together as they would develop models, as they would develop more integrated approaches to data and analysis, and perhaps even bring in the management community so that we could have integrated approaches between science, data analysis, and management systems. And education, of course, would be part of this as well. When we think of integration, this particular vision that was developed by Dr. Hauser actually on this call is one where land data assimilation systems can be used to bring about the integration process. For example, we observe nature with satellites, in situ measurements, and so forth. We can run them through a data assimilation system that has a Kalman filter associated with it that brings the data together. We can also feed into this predictions of what the state is anticipated to be when we have these observations to fill in the gaps. And then this will provide us with a new assessment of what the current conditions are, and we can then use that to initialize the prediction system, develop a new prediction for a future time step, and then observe nature again and use that to condition our prediction with a new data assimilation product. So this has been a very important development, thanks in measure to Dr. Hauser, to advance the concept of bringing data together from satellites, from in situ measurements, and in models. We also have within this strategy a component that deals with capacity building, and it will build on three main areas that have already had some development work ongoing: Latin and South America, Africa, and Southeast Asia. And the idea is that we will promote the transfer of technologies and capabilities across these three regions so that what's learned in one region will be applied in other regions. In terms of the mechanism for these discussions, we do have a integrated global water cycle observations community of practice, which anyone is free to join. It has a development component, a demonstration component for tools and applications, a capacity development component, and we have regional communities of practice associated with different geographical regions such as Asia or Africa. Again, this mechanism is likely to help us move forward in the next decade as well as serving us in the present. Finally, let me talk about a few next steps in connection with this development. We are working on this water strategy report, which we hope to submit to the GEOSS Summit in January 2014. At that point, we'll seek feedbacks and commitments from the members of GEO, which are countries and are able to fund activities, as well as international organizations. And then the commitments that we have will be consolidated into an action plan, which will then be tracked through the GEO work plan and through other mechanisms.